Hey everybody, welcome back. In this video, we are going over something known as Newton's second law. That's one of Isaac Newton's fundamental laws of motion. Now, depending on the class, you may have already been introduced to this definition. We're actually in this video going to focus on this part right here, what this has to do with total force. But we'll actually do that after reminding ourselves what the law says in the first place, okay? Here's the definition of Newton's second law. It says that the acceleration of an object is based on the force that's acting on it, as well as the object's mass. If that kind of sounds like an equation, that's because it is. Newton's second law is describing how you basically calculate how quickly an object accelerates. We learned that acceleration is speeding up or slowing down. So what determines how much an object accelerates? It's based on how much force, how much of a push or pull there is on an object, divided by the mass, how massive that object is. Now, as we've seen for all of our other equations, scientists are lazy. They don't want to write out the whole word, so we use A for acceleration, force for F for force, and M for mass. Now, this is the equation that represents Newton's second law, and to be honest, in my own class, I use this equation maybe more than any other form, but another common way this is written is like right here, F equals ma. These two things, they are the same equation. The only difference is we've taken this original one and we did a little bit of algebra. We multiplied both sides by mass to solve for F, okay? But these are the exact same equation. It's the same three variables. Oftentimes in my own class, you're going to be using this one, but either one is fine. Just this one is also very common. You might see it on online resources and future textbooks, things like that. But this is the equation that represents Newton's second law. So, okay, with all that said, doesn't seem too bad. You're saying here that you accelerate if there's a force, and as long as an object has mass, fine. To be honest, team, I'm maybe going to ruin our day because I have here a little demonstration, okay? This is a cart that has some amount of mass. Here is a person with some amount of force. It actually labels that force here. When I have this person right here, I'm going to hit go. Let's see what happens. Notice that the speed gets more and more and more. It's accelerating. I hit pause. Well, that makes sense. Nothing super interesting right there. I'm going to make one little change. I'm going to add another person on this side. They are also applying a force. And then I'm going to hit go. Here we are. Okay, I've hit go. They're both pulling. Is the object accelerating? Uh-oh. Team, we seem to have a bit of a problem. I have forces being applied to this object, right? I have 150 newtons. Heck, I even have another 150. But now, even though there are forces and this object still has mass, I'm going to hit go again. Now it's not accelerating. If you think I'm lying to you here, it's still playing. I'm going to remove this person. Oh, weird. While I have forces and while I have mass, there seems to be a problem. Suddenly, even though I have force and even though I have mass, there doesn't seem to be an acceleration. That seems contradictory to what this equation says, and that's a very important thing, team. This actual definition actually needs a revision. I'm sorry, it's not quite as simple as saying that acceleration is based on force and mass. Hopefully that website showed it to you. Again, while there were forces acting on that cart, it wasn't accelerating. Why not? It turns out, everybody, that the acceleration of an object is actually based on the total force. And that might not be something we've talked about, at least if you're in my own class. It has to do with the total amount of force acting on it. So I've rewritten my equation. It looks similar to the older version. Here I have A, here I have force, here I have M. But this isn't just any old force. It's referring to the total. And when I say total, it means what it sounds like. Total is like the overall amount when you add everything together. Okay, it's not just based on if there's one force. It has to do with all the forces that might be acting on an object. FYI, and I'm sorry that there's maybe not one always consistent word, but you might see other words used, or you might hear a teacher or somebody use other words. Instead of saying the total force, you might hear it phrased as unbalanced forces. If there's an unbalanced force, that means it will accelerate. Another word for total is net. Net is also meaning when you add things up. So some textbooks might say, oh, it's the net force divided by mass. Total also means the sum. You add things together. It's based on all those forces. Okay, one last one. It's the non-zero. It turns out, team, just like that example I showed with that online simulator, if the forces are canceling, well, that gives you an overall force of 0, and that's why you don't accelerate. So it begs the question, how do I figure out this total force? That's what we need to do. Okay, it's not tough, but it's worth going over a couple of examples. I've made a free body diagram, an FBD. Hopefully that sounds familiar when I say that, an FBD. This object has two forces. I don't know, maybe it's like a space probe in the middle of outer space. There is a 10 Newton thruster acting on it. There's also a 3 Newton thruster, and they're acting in the same direction. Question. What do you think the total force is for this setup right here? What's the total? The total is 13, and maybe you guessed that intrinsically without me even going over a definition. That makes sense because they're both acting in the same direction. Imagine you're trying to move something that's really heavy, and you need like a friend to help out. Like if you're both trying to move something heavy, let's say you're trying to move it this way, you're both gonna apply forces in that same direction, because when you and a friend are pushing on an object in the same direction, the overall amount of force builds up. So that's something you need to know. If you have forces in the same direction, you're gonna add them together. Here's another example in yellow up here. Again, maybe it's a space probe in outer space. There's a 10 Newton thruster going this way to the right, a 3 Newton thruster to the left. What do you think the total force is in this situation? Now the total force is 7. Maybe you guessed that. If not, that's okay. But now we're going to subtract 10 minus 3. That's how I got 7. Why? Because if you have forces fighting one another, this is like playing tug of war. You are pulling one way, your friend's pulling the other way. You are fighting one another. It turns out those forces will cancel out. They will subtract. So if there are multiple forces acting on an object, you have a little pre-job to do before you could actually use this equation. You might have to figure out what is the total force, okay? I'm going to end with an example question. This is my last slide, okay? I recommend you hit pause and you try it on your own. You can do it by yourself, but I'll of course go over it as well. Here's what it says. A 50-kilogram skydiver jumps out of a plane and falls to Earth. Here's a picture. Before they deploy their parachutes, they experience an upward drag force of 250 newtons. So even when objects are just falling, they experience a kind of air resistance, a type of drag. Obviously, a parachute will make it even more, but even without the parachute, there's some drag force, and it says here in this problem, it's equal to 250 newtons. The weight of the skydiver, it tells us, is 490. Calculate the acceleration. All right, again, I recommend you hit pause and you try it on your own. If I'm trying to find the acceleration, this is the equation I want to use. This is Newton's second law. Here's acceleration, here's total force, here's the mass. This is what I'm going to use to calculate that acceleration. Now, I know you didn't have to draw this. It doesn't say to do it in the problem, but drawing an FBD, while maybe not always required, is a good way to help you visualize how the forces are acting. Because if you remember from the last slide, sometimes we're going to add forces, sometimes we're going to subtract. So here I've diagrammed the upward drag force, and it even says in the problem it's upward. You didn't have to know that intrinsically. The downward force is weight. Weight is always down. So if I need to figure out the total force, what is it? What do? Because they're fighting one another, you're going to subtract. So I did 490 minus 250. I get the answer of 240. If you're asking yourself, wait, could I do 250 minus 490? Could I subtract them the other way? Yes. And in high school physics, that's totally fine. You will probably see a negative number get spit out, and that's fine. You can plug in negative numbers into this equation, so it doesn't really matter, again, in our high school level physics class, which way you subtract these. But the total force is 240. Well, okay, now I'm going to plug into this equation, and that's what this is showing right here. This is nothing brand new. What I'm doing is I'm taking the total force, 240, and I should be dividing it by the mass. The mass is 50. Remember, mass and weight are different things. So I should be doing total force divided by mass. the total force is 240, the mass is 50. So in my calculator, I should do 240 divided by 50, and I get 4.8. That's the acceleration, 4.8 meters per second squared. So this equation can be used to calculate acceleration as well as other things, but also if there are multiple forces acting on an object, you need to determine the total force. And you find the total force by adding forces if they're in the same direction, or by subtracting forces if they're in opposite directions. Okay, that's all I got. Thanks a lot for watching.